Animation curves is one of the beginner's nightmare, but I want them to become your best friends. To display the animation curve of our ball, let's go into the graph editor. Right now, our curves looks a bit boxy, not really curved, and this is because we are still in constant interpolation, but it will help us reading them. The curves are just a graphical representation of a value over time. The yellow controller points are currently the different keyframe we have inserted before. If I select the yellow point on the blue curve at frame 7, it has a value of 4, such as the Z location of our ball. And if I now display all the object transform channel in the graph editor, we can see that the Z location is highlighted. So the control point I've selected in the graph editor is the keyframe value of the Z location of our ball. If I double click on one of these channels, it will select all the control points of the current curve. You can hide and unhide curve as you would do with any object in the 3D view. If I press Shift H, I will hide everything but the selected curve. Or you can click on the little eye icon to choose whether you want to see or not the curve. With G, I can move the curve. I can press G and Y to constrain the movement on the Y-axis, or GX to constrain on the X-axis. Before we start reading those curves, let's get rid of any of the curve we don't need. Since our ball is not rotating, we can get rid of all the Euler rotation curve by pressing X, and we can also get rid of the X and Y location, since our ball is just moving up and down. This is a good practice to get rid of any unwanted channel to keep your graph editor clean. We can find the Z location corresponding value onto the controller point of the curve, but also in the transform channel of the object. Pressing the N key will open the F-curve panel. This is a little N here to check the position, value, and interpolation mode of the keyframe channel. Let's now select all the keyframes, press T, and switch to Bezier interpolation. If we now play the animation, we get a way smoother motion of the ball. When you switch from step mode to Bezier mode or curve mode, we call this the splining stage. If we have a quick look to our curve now, we can see that the Z location curve is getting a higher value when the ball is getting higher. I will unhide the scale channel by clicking the eye icon. I will select the first controller point of those curves and press the dot key on the numpad to zoom on it. We can easily identify the Z scale channel, which is in blue, and allow us to control the height of the ball. And the X and Y that are one on top of the other that allow us to control the width of the ball. Let's check a couple of examples to betterly understand the behavior of the curves. In this example, the curve is controlling the rotation of the arrow from a value of minus 90 degrees to plus 90 degrees. The curve is raising rapidly before easing into the frame number 24. And when we scrub through the animation, we can see that we have a big spacing in the beginning of the animation and it gets lower in the end. Using the motion path, we will have a preview on the spacing of this animation. And now we can obviously see the difference of spacing during the animation. And the more vertical the curve is, the larger the spacing. The more horizontal it gets, the smaller the spacing is. In other words, the more vertical the curve, the faster the animation, the more horizontal, the slower. In the next example, let's consider the X location curve of the ball being the time. It goes forward in a linear fashion. Now, if I activate the Z location curve and I frame it properly, look at how the Z location curve and the motion path we own in the 3D viewport align or are comparable. Again, when the curve is vertical, the sphere rises rapidly. And as the curve gets more horizontal, the sphere rises slower. So if I now give an S shape to my curve, the ball will move slowly in the beginning, then in the middle of the animation it will accelerate as the curve gets more vertical, and in the end it will slow down. We are creating an easing out from the frame 0 into an easing in the frame 24. And since we still have the linear motion of the sphere on its x-axis, we can see that the z-curve really looks like the motion path of the sphere. Since my sphere is moving on the x location in a linear fashion, any modification I will add to the z-curve will show in the 3D view as in the graph editor by updating the motion path. You can use the few examples available in the file to play with the curve, recalculate the motion path, and check out the spacing. Back to the rotation example, I've modeled the curve so that I have a fast acceleration in the beginning, then a plateau, and then an ease out and ease in. And it absolutely reflects on the motion path. The pretty vertical shape of the curve on the first two frames generate a big spacing. The plateau shape or flat shape of the curve indicate that the value is not changing over time, so the arrow will stop. While the final S shape of the curve shows an acceleration, then a deceleration into the final frame. To summarize, we have seen that a curve is just a representation of the evolution of a value over time. The more vertical the curve shape, the faster the value change. And it translates in bigger spacing. The more horizontal the curve, the slower the change. Motion-wise, it translates in smaller spacing. A flat curve indicates that there is absolutely no change in the value, and so no motion.